So, wer von euch hat denn auf dem 37C
Who of you has seen the talk on this 37C3 about Euclid, the space telescope? Yes, that's been quite a few people. Very nice. Today, we'll get an update to the newest developments and specifically new pictures from the space telescope. The talk is called Euclid, the Space Telescope. 180 million galaxies are a good start. This talk is held by Knut Janke, and please give it up to Knut Janke. Thank you. Yes, thank you very much. I am happy that to this very early hour, so many people are here. I'm happy to be here again. A year ago, Euclid had been in space for half a year, and we were happy that everything was working. The start went well, launch went well, the instruments worked. We had first pictures, that was awesome. Now we have a year of routine and of science, and we've got some data, 200 million galaxies. That's just a nice number, isn't it? But I think this is also a good time to look at what happened in this time. This telescope was a theoretical construct until now, and now it's actually here. We'll give you a view behind the scenes, and you'll see some pretty pictures, and also hints at where you can look at a lot more pictures than today. I am Knut Janke, like I said, and I'm an astrophysicist at the Max Planck Institute for Astrophysics in Heidelberg, in the Euclid consortium that runs the telescope and has built the telescope. I am one of the 3 instrument scientists that are the interface between the hardware of the instruments and the astrophysics. And I also lead a group on super mass black holes, which is distinct from this project. So we have 3 parts in this talk that I'll talk about. What happened so far, what is Euclid, what are we trying to do, why do we need a new telescope since we had some few already, what are the challenges that we saw during the year, and then finally a couple of nice pictures. So what does Euclid actually do? Hank Hoekstra, my colleague, summarized this in saying, we look in a dark room, we look for a dark cat where we don't actually know that it's there even to begin with. That's cryptic, isn't it? It's almost as cryptic as that what we actually try to do. We look for dark energy. We try to limit the theories for dark or around dark energy. Look at the websites for the consortium. We know how much energy and mass is distributed throughout the university, and mass equals energy, as by Einstein. And the largest part of it, we don't know what it is. And so usually, we know mass is gravitation, and it attracts things. 70% of the energy density in the universe does not actually attract, but it repels. The expansion of the universe, it doesn't slow down. It actually accelerates. Everything accelerates, and we don't know what is doing that. So what we do know is we have a lot of theory families, let's call them, that try to get where dark energy comes from. General relativity theory from Einstein. There is a constant in there that might be where you can put this energy in, or maybe other corners. And all these theories make very different predictions. as to how the universe expanded in the past and how the building of structures in the universe and building of galaxies, how that happened. And we want to measure that. That is what Euclid tries to do. We look at the building of structures back in time. We look at the expansion history of the universe. And for that, we measure about 2 billion galaxies. So we have 10% of that. We measure the three-dimensional positions and also the form. No details, but what we need is a view into space. We need charting 2 billion galaxies. We look at a third of the sky with very detailed pictures.
So we have a map here. We look at everything that's not the Milky Way. That's the bright band in the middle. There's too much stars, too much dust. We can't see there. And we don't look at the same plane as our solar system because there's too much reflection as well. But we look at everything else. And that's where those 2 billion galaxies are. We have to look very far, but okay. Why a new telescope? Well, we could use James Webb Telescope or Hubble, both of them up there. Hubble for more than 30 years, JWST for 3 years. The problem is they only look at very small windows of space, but very deeply. So if we compare it to the moon, we could take lots of pictures, put them together like a mosaic and have a whole picture. But if we do that with 13,000 pictures, we would need a couple of hundred years because of all the space that is there. So we need something faster. So we need a new telescope. That's not fancy with their cameras. It should be very simple, but it should be able to see the forms and the age of galaxies very, very nicely. So we need a lot more field of view with the telescope than we can do with the things that already exist. So that's why we need a new telescope. So this is a mirror telescope that has like 1.20 meters of circumference. It's not very big for an earthbound telescope, but for a space telescope, very big. We have an infrared instrument and this spectral analysis. We have 67 megapixels of detectors, and we have a visible light camera this with over 609 megapixels per image. With those, we can take very clear pictures. It took a long time. We had development time over 20 years, 10 years of hardware development, and if it's done, all the things sit in this box, the telescope on top, the mirror on the side. This is a pretty small telescope, but we have like a minivan of hardware that needs to get to space. And to do that, we had to do a lot of work. It's a mission of the European Space Agency, ESA, in coordination with a consortium that spans Europe, Canada, the US, and Japan. More than 2,000 people. It's not an abstract thing. It's a real thing with real people, many real people that work very closely together over lots of years. And I am part of that. We did build the instruments. We got the budget, funded the instruments, and we do scientific data analysis, and we do the science on it. And all of that is the consortium. So in the end, that's me. About a year ago, nearly 2 years ago, I was fortunate enough to see the whole telescope in the clean room. It's 4 meters high. The perspective is a bitch. So then it got really fast. 1st of July, 1.5 years ago, Euclid started into space. We used a large US-based space agency for that. It went to orbit 1.5 million kilometers from Earth on the far side to the Sun, and it travels around the Sun with Earth. It's a very stable point in space, like temperature-wise, to get the best and clearest pictures. So, it's in space. Everything worked like a charm. So, 99%, yep. But, of course, you don't just go about doing such a mission. There's years and years of experience of space development and how to bring stuff to space. How do we build stuff that works in the cold, that works in a vacuum, that don't care about radiation that gets to you? How do you do electronics? How do you do software? How do you build stuff that doesn't just error out if there's an error? So some things do surprise you, and they're getting it down for the next mission. So we did have some issues. For example, and that's one of our early pictures, and you can very nicely see the structure of the WIS camera. That's one of the detectors. There's a lot of 4K by 4K detectors. They're just read in like quadrants, and all these dots are bright stars. We see stars, we see the sky, good. But if we take a closer look, we see some other stuff like those things, and that's sunlight. And if there's one thing we don't want in our pictures, it's sunlight. Where does it come from? And it was pretty clear it doesn't get in through the telescope. So in our terms, it's a non-nominal light path, so a hole. And over time, we found out what the reason for that was. This is an animation of the telescope. There's a sun shield on the back, and it should always be facing the sun to shield sunlight from getting to the telescope. That's our telescope. There's the instruments, and there's this little booster that's for stabilization of the position in space. It just goes to come around this thing, and this thing has lights. Usually it's facing the sun, but there's some radial distortion that we need, and there's a little beam of light going there. And back there in the box is the instrument, and there's a light path that gets shown in there. So there was air inside, and that had to be blown out, and there were many layers of foil to keep that clean. And on one of those places, there was a hole, and through mirroring, those streams were created, and we could make out where this comes from. So we know the sun is very, very bright, and our instruments are very sensitive, and so a percent of a percent was enough to create those distortions.
So we found a solution. What we do is we turn the telescope by a few degrees. We can't quite do the survey as we wanted to do, but we'll put the telescope in the shade, and you can see before and after. It's wonderful. No more traces of the sun. Applause, applause, applause. And in this process, a lot of people were part of to diagnose this, to say, yes, we can find a solution, and then within 2 weeks, replan the sky survey. That was a lot of effort, but it did work, and now we see a lot of stars and a lot of galaxies. Awesome, that's how it's supposed to be. So, talking of the sun, this is the second challenge. The sun doesn't just make visible light, it also makes X-rays, specifically when there's eruptions on the sun. So there's a solar cycle, if you have heard about it, a solar cycle of activity every 10, 15 years. It goes up and down, the activity, and right now the sun is at the maximum in their activity. So your telescope will show nice sun dots, spots. Sometimes you might see an eruption, and that comes with X-rays. So what we've discovered is with X-rays and this installation is we're looking at our field of view, and we see weird structures. The background is nice, but in the details there's odd structures that you can see, shade and so when we looked at this non-distorted, we saw cables as shadows. Yes, cables as shadows. Why? Well, this is the sun shield. This is the solar panels, and these are the boundaries between the two solar modules. And here, where that red circle is, that is where the instrument sits. And if you put this side by side, solar cell and the part between, you find a perfect picture of this. This is the only part where the X-ray dimming was not thick enough. Okay, good. So what we have the diagnosis. What do we do? Well, we ignore it because these strong X-ray flares only happen every couple of weeks for an hour or two. That means 10% of the data from that one picture is gone. That's okay, we can deal with that. But it's something that was really unexpected. So if you look at that, these elements, then take care of that. There's a third challenge. We have these two cameras. This is a CAD rendering of where the instruments are. The telescope is standing on its head. Telescope is going down. Where these lines are, the light comes in, and there's a fold mirror. There's a secondary and primary and a tertiary mirror. The light goes through a dichroic element that passes the infrared light and mirrors everything else away, and that goes to the vis camera. Okay, nice. So what we knew is that there will be moisture somewhere. The telescope is built on Earth. It gets shipped from somewhere. It's in the atmosphere. And atmosphere can only be cannot be infinitely non-moist. Yes, it's always going to be something like 10% of moisture, and you don't want to have too little moisture in there that gives you static electricity, and that's a problem. This gold foil is aluminized Kunststoff that can actually attract moisture up to a certain percentage of its weight, if you've ever been in the areas where you launch a rocket, there is moisture everywhere, and we knew there would be moisture everywhere. And once the telescope is in space, it will condense and it will turn into ice somewhere. We knew that. The previous mission of Gaia measured star positions, and they had a very surprising problem with moisture. So we've been warned by Gaia. So the question is only what will the effect be? We had procedures how we would warm up parts of the mirrors and so on and so forth. To turn the microscope toward the sun to evaporate the moisture and so forth. But first of all, we wanted to know what happened after launch. So what did happen? So this is what happened. This is the vis camera. We saw for the infrared camera nothing happened. The performance did not go down. It was fine. Apparently, ice didn't absorb in the infrared. So the vis camera, we saw, comparing this to the theoretical performance or the theoretical brightness of objects, a few months after start, you can see November 23 to November 24. It was for a few percent beneath the theoretical performance. Probably it was at 100% right after launch. So we'll look at that. We'll follow that and see if it turns into a problem. So it goes down. Okay, something is happening here. Things that are happening and changing, that's seldom a good sign, but we knew what this was going to be. So what happens later, okay, this is going down even further, or okay, we need to do one of these decontamination things and we'll take the folded mirror number 3, the only thing that the vis camera 3 singles out, and we'll warm that one up. When it's a problem. Okay, good. Okay, seems good. Okay, we've lost 15%, fine. We'll warm it up for a few hours at 115 kelvins. That should sublimate away, and we should have a nice mirror. Bing. Okay, that's awesome. That's just like we thought it would be. That's awesome. Now what happens? The question is, is this going to be a procedure for every half year, or will it just stay like that? So what did happen is version 3. No one understood what this was. It was worse. It turned worse and worse and worse. This is not good for science. But we knew that warming up would work. It would only take a few hours. We could do this every few weeks to get back to 100%. So we've done it, and we're back to 100%. Okay, now predictions got more unsharp. Is it going to be the same as in the beginning? We had a version 3. It stayed constant.
So, in the end, that's a situation we can work with. Very small changes over more than half a year. We don't think anything's going to happen there. Our explanation for this is that it would be nice if heating up something, you just heat up the mirror. But actually, the things holding the mirror also got warmer, and there's a structure there. There's mechanics there. There's isolation, so maybe we warmed up some of the insulation, and that just moved inside of the instrument and came back. And so more moisture came back from all the other places the foil could reach. But the second time, the same thing didn't happen. There wasn't any more moisture, so all went good. So we were prepared for that. We knew that because we had to think of that because of Gaia. So some things done, 3 things solved. So now we know we can start routine. We can go into routine operations, get scientific data, throw it into our pipeline, and we are doing that. And that's why we have like 200 million galaxies now in the scientific quality. So let's look at nice pictures. Just short trigger warning. If your things change very quickly, if you can't deal with that, look away. So per position in the sky, we make 4 to 6 pictures with slight changes in the racial distortion. So we have a field of view, and all those white and black lines are just borders in the between the detectors. We took some different size galaxies. There's lots of data. Everything looks like that. We have impacts of cosmic radiation, but with 4 to 6 images, we can use the median or can look for those impacts and mask them or just calculate them out. So end of trigger warning. So one of the things we did last year, I could show some of the pictures, early release pictures. They were made exactly for that. Just a few nice pictures to get early images for the public. To just show off the science. We did 14 of those with one position each. We had like 70 minutes of exposure, some a little bit longer, with both cameras, infrared and visual lights. We just took the data, the pipeline wasn't ready yet, and we did the first scientific publications. So the second half of the pictures are a little bit hidden, but we can use them to show what Euclid is good for. And that's one problem with our PR. If you show a couple of pictures, well, nice. My amateur telescope can do this as well, because you can't see the details. You can't have a 600 megapixel image, look at that as a whole, and see the details as well. So we can play around with them. NGC 6744 is one of the very close spiral galaxies. It's part of the new general catalog. It's a catalog of nebulas that are very close to the Milky Way. And if you look at that, you can see basically everything that Euclid can do. This is a reverse color image. We have like 2 channels of the red band colors and 2 bands of blue color, and they're inverted. All those shining things are stars in our Milky Way. They're in the foreground. This thing is a large spiral galaxy. You can see the core, you can see the spiral arms. We have 2 other galaxies up there. You have a spiral galaxy viewed from the side, so like a little bit tilted, like a pancake. And the things in the background, the red things, are galaxies that are very far away. But that's not the full field of view. That's just a part of the image. So, and this is the whole picture, which the thing was part of. Very, very large galaxy, 2 cores, 2 galaxies merging, and over the next 200 million years they will collide, and by gravitational interactions, stuff gets thrown out, and maybe no spiral arms are created, but things just get ejected. And there's hundreds of galaxies in the background, or thousands, and the far little dots are the things we actually want to do the science with. That's what we take pictures of, 200 billion of them. But astronomical analysis can be done with all those galaxies that we can see here. But that's not the big spiral galaxy. That's also just a part of the true image. And this little square was the picture, and this is NGC 6744. And it's no coincidence that this fits exactly this picture. It was chosen for that. So, but it shows that that's the first picture we can use the data of, and just 1% of the data will be used for more than for the science, and we will take tens of thousands of images like that, and you can imagine the amounts of science we can do with that. So another picture, something completely different. We chose Messier 74 in our own Milky Way, only 1,300 light years away in our own galaxy, and it's a starburst area, and stars are created here. So basically everything we can't see in faraway galaxies, we try to see in our Milky Way. Everything that's bright in this image is dust. So because dust absorbs the light, the blue light, we see see dust as red. And we can see a lot of very young stars. They're just being created there. And whenever stars are created, they also create lots of dust. And they're very small molecules just in space. And the things we see in the background here, that's just stars in our own galaxy. So we have like 80,000 stars in this picture. And if you look at the details, then you can see what kind of area this is. They're very hot stars, ionized gases, gas pressures. You can see that through some kind of overpressure, dust got ejected. There are just bubbles forming because of some effects. There's lots of dust all around, absorbing the light. Just like on New Year's, if you look through all the gases of the fireworks. And in the second picture, much more intensive, the gases haven't been ejected yet, and you can kind of see what happens there, smaller ejections. And where there's no gas, you can see the background of the Milky Way. And a third picture, on the completely different end of the spectrum, there's lots of galaxies again, tens, hundreds, thousands of galaxies that interact via gravity. And they're just part of the large structure of the universe, and they just were evolved over time. Many pictures of Euclid look like this, because you have to look very, very closely to get the details. And if you take a picture like this, then so everything that looks like very diffuse are galaxies from this galaxy cluster. And if you look closer, you see those bows, those lengthy kind of things. Those are galaxies that are behind the galaxy cluster. And mass bends space. Light follows this bent space on straight lines. So the galaxy cluster acts like a lens and bends the galaxy in those lengthy stripes, and just because they're just directly behind the galaxy cluster. And that's why we get those pictures, and that's called gravitational lensing. And everything we look at by human eye with artificial intelligence, and by using this lensing effect, we can calculate the mass of the galaxy cluster.
So someone took this picture, thought about, well, let's do this different and sort galaxies by brightness, the first 3,000 maybe, and if I had another half hour, I could show you the first 3,000 galaxies, and we could look at details and the next field and the next field. Well, we're not going to do that. Instead, much better, you can take a look at your home, and that's better for you and for the data. So this picture has gone through press and through the blogs. It's a zoom of ESA into the first % of our data. It's 1% of all of our data. And there is a magnification until factor of, I don't know, 1.5 million people have looked at this. We like your interest. Look at this for 2 minutes. What I personally find even more interesting is ESA Sky. It's an online page where you can take a look at the entire sky, and this entire sky also has the 14 Euclid images. So you go there to Sky ESA int, you click here, and you'll get the selection of the 14 pictures and pan and zoom. You're gonna need some time. So what's next? So we have 10% of our survey done, but the calibration of the data will take a while. We now have the first 53 square degrees. We're done with those. They're at the consortium for the scientific evaluation, and they go to the world. Everyone can take this data and do science on them, use the raw data, do something with it. They'll go to the world on the 19th of March 2025. And there's already 40 articles that will appear about this, but there's more science in there. There's going to be big data releases in 26, 28, and 31 until hopefully we have all the data, all the sky survey complete. It will be a database for the next 20, 30 years for science. For like, you need a good picture of this position, you just go to the archive and fetch it. Here's already, I mean, a few articles have been published already. A few cosmologic results will be coming in 26. We're really curious what that will show. And there will be more science and research in the next few years, unless we get some surprises that we saw and solved. So what we know, Euclid works. It works really well. We're scanning 10 square degrees a day. Science has started. There's pictures and infos at these web pages, and yeah, social media. Thank you very much for your interest.
Und ich habe überzogen.
Oh, I'm over my time. Thank you very much for this good talk. There's a little bit of time for questions. Please come to the microphones.
Alles klar. Als erste Frage hätte ich eine vom Signal Angel.
So, the Signal Angel, please. Hello, thank you very much for this good talk. My question is about your process of finding problems. When you find something like this light path, how do you debug that? Do you have a second telescope on Earth, or how do you do that?
We don't have like duplicates on Earth. For some electronics, we do have that. Software, of course, but we have very lots of experts who know about the stuff, and they think about and look into where could this come from, where should the light come from for this to happen, and that's basically how we did this in a week to isolate this specific problem. And with other things, the same thing. We have lots of people we can tell about the problems, and they solve it.
Zeit für eine kurze Frage. Mikrofon 1, bitte.
Okay.
Only one question. I have two. Okay. So what I would really like to know is, someone wants to go to Mars. This guy who built this rocket. Does anyone want to go to L2 to maybe repair or maintain stuff that's been positioned there, or does it even make sense?
So the question is for repairability to the faraway orbits. By humans, no. For robots, yes. NASA has a directive to do that. They want to have all their missions repairable in the future. So there have to be docking modules. There have to be maintenance hatches, modularization of instruments. I don't know about ESA, but we're not sure if repairability is the best option. Maybe we just put something new up every 10 years.
Yeah, like if what you've built doesn't work, so much money will be lost.
So the aim of the 20 years of development is no catastrophic failures, and we did that.
Thanks for listening to the English translation of Euclid, the Space Telescope at the W3C. Your translators were IT Bain and Gunis Burrow.